Section 4.5, we're going to use a lot of what we've learned to spend some time graphing functions using calculus, and it's going to bring together everything that you've learned, not just in this class, but every math class up till now. We're going to look at the domain of a function. You can look at things such as, does it have any symmetry? Is it an even function? Is it an odd function? So Nina, if it's an even function, what's that mean in terms of the graph? How does it look? Can you give me an example of an even function? There's one. Parabola. All right, parabolas are symmetric with respect to the y-axis. Same with cosine functions. So if you have that symmetry, that's nice. That cuts in half the amount of work that you have to do. Here's your tricks for rational functions. We mentioned that in the last section. Asymptotes, horizontal asymptotes, oblique asymptotes, intercepts. I like you to find your intercepts. So setting x equal to 0 and setting y equal to 0. Definitely, you should be concentrating on the calculus part of things. Your critical points. Where does the derivative equal 0, or where does it not exist? Intervals of increasing, decreasing, concave up and concave down. All this needs to blend together to give you a nice picture of a graph. So we'll start with a couple simple ones. And I guess my goal here is more quality and less quantity. So we're not going to do too many here. We're just going to try and put a few together in a nice orderly fashion. We'll start out with problem number 4. So everyone's got the handout, right? Okay. Problem number 4, y equals x to the 4th minus 8x squared plus 8. Y'all got the handout, but I can't find mine at the moment. You got an extra one? Thank you, sir. So, first thing we'll do is we'll look at the domain of our function. And because it's a nice polynomial function, that means the domain is everything. So the domain is negative infinity to infinity. Okay. No, if you put, I like that actually. I like the script R. No, I like that. It's just not notation that I expect everyone to know, but that's actually a nice, cool notation. Well, this isn't going to have a lot of interesting points because it is just a nice little polynomial function, but there are a few things that we should look for. For instance, let's start out with the first derivative here. First derivative is going to be 4x cubed minus 16x. And what's the first derivative tell us? Yeah, it tells us where our function is increasing or decreasing. So, okay. Now to know where it's increasing or decreasing, I need to know where it's positive or negative. It can change signs where the function has roots. So I need to find roots of this. I'll factor out the 4x. That leaves behind x squared minus 4, which further factors into 4x times x plus 2 and x minus 2. We should be able to read off the roots from this polynomial. Where does this actually equal 0? Good. 0, negative 2, and 2. All right, looking good. Let's keep going a little bit further and find out some things about the second derivative, and we'll start doing some more testing. So our second derivative, y double prime, is going to be 12x squared minus 16, and I'm going to want to know where that's equal to 0. So y double prime equals 0 when 12x squared minus 16 equals 0. 16 over 12 reduces to 4/3. If I take the square root on both sides, I'll end up with plus or minus 2 over the square root of 3. Now, if you want to rationalize that, that's fine. It's okay by me. But I'm not going to rationalize it. I'm just going to leave it as is. I'm trying to think. It's going to be about 1.15 or something like that. In any case, let's start using some of these points that we're finding from our function and then matching things up to our curves. We're going to make a couple little tables here. X, F, F prime. Let's see, what points do I want to put in here? I want 0, -2, and 2. So let's put them in order. And I'm just going to spin this around for a second here. Help myself out. Sorry if I'm making you dizzy. Bless you. And let's see, I guess I need it for y double prime as well. There's 2 points there. So there we go. Okay, so let's list our points. We've got -2, 0, and 2. And at these points, the derivative is 0. So we're going to expect either a maximum point, a minimum point, or an inflection point. And we'll do likewise over here. X, F, and F double prime. And let's see here. We have points at 2 over the square root of 3. It's going to be -2 over the square root of 3 and 2 over the square root of 3. I'm going to put those into F double prime. I have zeros there and there. Let's put things into our function and find what these points are here. So I'm going to put in the original function, x to the 4th. Well, no, we're not going to test in the original equation. I guess we can put in the function and the derivatives as well if we want. X to the 4th minus 8x squared plus 8. So there's the function. And, you know, it's a good idea. Let's put in the derivative and second derivative as well. So the next one is going to be 4x cubed minus 16x. And finally, 12x squared minus 16. So I've got all three functions in my calculator. But right now, I just want to look at the actual function. So I'm going to shut these two off, cursor up to the equal sign, and press enter there. I want to know what's the y value at -2, what's the y value at 0. Well, the y value at 0 should be pretty clear. Can you tell me what the y value of 0 is? 8. Yeah, should be 8. You should be able to just see that. So we'll double check. 0 gives us 8. No big surprise there. But we'll do a couple more functions, like -2 and 2. And so both of these give me -8. Okay. Let's type in some more functions. like there are some more points, like negative 2 over the square root of 3. And it's going to give me an ugly decimal value, at least initially. Negative 2 divided by the square root of 3. We'll get negative 0.888888, etc. Does anyone recognize what this is probably going to be if you actually evaluate it all out? No, the number. It's a fraction. If you don't, that's fine. Negative 8/9. And likewise, the other point's also going to give me 8/9. So 2 divided by the square root of 3. Same thing. Negative 8/9. So there's a couple things that we can do with our graph. We can put in a few of these points. We've got them. So on our graph paper, let's see here. Negative 2 and negative 8. That's going to be down here someplace. So about here. And 2 and negative 8. It's going to be about there. Now your other 2 points here, these possible inflection points, they're already graphed for you. Those are here and here. So those points are graphed. There's one last point that I should put in here, and that's 0 and 8. That's going to go up about here. About 4/5 of the way between 0 and 10. So far we got kind of a crazy looking graph here. We got to connect these in a logical way. So to do that, it would help out to know if this function is increasing or decreasing, concave up or concave down, and where so and how. How can we figure that out? What tells us where a function is increasing and decreasing? Yeah, where a function is positive or negative in terms of its derivative. So let's turn on our derivative and shut off the function. I recommend that you shut off the function because sometimes people get confused. They look at the wrong thing. So you take your cursor and you put it on the equal sign and you press enter. Now if the equal sign is emboldened like this, and then it's turned on. If I do the reverse, then it's shut off. So now nothing will show up in my tables if I go to the tables. See, I don't get any y values. I just get the x values. So let me go back here and turn on the derivative. So I press that and go to the tables. I need to test some points. What would be some good test points? Negative 3, negative 1, 1, and 3. And the important information that I need here is right here, the signs. Negative, positive, negative, positive. So negative, positive, negative, positive. Now that tells us some things about our functions. So, Veronica, what's that telling me about our functions here? Decreasing. Good. Decreasing, increasing, decreasing, increasing. Cool. So we got that part taken care of. Let's go over here and take care of this one. So I'll come back here, and again, I'm going to shut off the second or the first derivative this time. Work with the second derivative. So go down here and go to the table. Let me delete all these values here. I'm using the delete key to get rid of those. I need some more test points. Now, that's a little bit harder. Let's keep in mind that this is about negative 1.15. This is about 1.15. So, Katie, what would be some good test points I can use around these? Sure. -2, 0, and 2. Sure. So I end up with positive, negative, positive. What's that tell me about my function? Concave up, down, and up. So you're starting to build a picture of this function, and it's telling you a few things about these points. What's it tell me about -2 as a point? What can I see from that? Tau? So it's decreasing and then starts increasing. So what's happening to it? It's a local min. Good. So the first one here, that's a local min. All right, good. It's a local min. How about this one? Increasing and then decreasing. Local max. And then local min again. Now over here, something different's happening. The concavity is changing from concave up to concave down. That makes this an inflection point. Actually, they're both inflection points. Both of those are inflection points. Places where the shape of the curve changes. All right. I think we've got all that we can get out of this. Now it's time to draw it. So let's put all that together and play connect the dots in a logical way. Now there's nothing wrong with actually looking at the graph. In fact, I think I sent you a link for Desmos earlier. And let's look at it here. Here's your inflection points. And you got minimums and maximums. So does this match all of what we expected? Well, increasing and decreasing it certainly does. But what's going on right here at that inflection point? Right here. Can you see anything happening here? The function changes its shape. It's got a concave up shape to the left of -2/√3, and between these 2 points, it's concave down. And then it starts concave up again. So kind of matches everything we expected. You've got your y-intercept here at 0, 8. We expected that as well. So on your handout, you can just play connect the dots. But you want to do it in a logical way. Don't just give me a nice little sawtooth kind of thing here. Give me something that resembles the function. Here. All right, not so bad. There's actually one other thing that I could have taken advantage of if I really wanted to. You notice that this function is symmetric. And that's because this is an even function. Now, I'm not going to go over how you check for even functions, but basically if f of -x equals f of x, then the function's even. You can look back in your algebra stuff to see that, or I can certainly give you some help finding that if you need it as well. Whew. Like I said, I'm going for quantity, or quality, not quantity here. Any thoughts on problem number 4? Other than, oh my God, I hope he doesn't give us like 8 of these on the exam. Yeah. Do you have a specific question there, or just need to finish copying things? Yeah. And this would also be an inflection point. Yeah, they both are. They're inflection points because the concavity changes. So you see it on the graph. Here's your inflection point. Inflection point. This is a local max. This is a local min. This is another local min. And actually, now looking at the graph, we can say more than their local mins, they're global mins, right? The function doesn't get lower than that at all. So there's actually global mins as well. Yeah. Yeah, because they're the same. Same height. Anything else on problem number 4? Let's try problem number 10. So one of the things that I do sometimes to make your life easier on an exam, especially when problems like this get really long, so just give you the first and second derivative. I'm like, okay, here you go. And my purpose in that is I want you to just tell me that, okay, I know the analysis. I can do the analysis. If I don't screw up with the derivative, then I can do the analysis. So your function is this. It's x squared plus 5x over 25 minus x squared. Now, one thing right away should jump out at you. Because this is a rational function, we might have some issues with it being defined everywhere. In fact, where is this not defined? Where is it? 5. Plus or minus 5. So our domain is everything but those 2 points. So our domain is x not equal to plus or minus 5. So we're just going to throw those out. Those aren't part of our domains. You can't have critical points there. You can't have inflection points there. It's just not in the graph. In fact, what do we expect when we look at this graph? What do you kind of expect at 5 or negative 5? Yeah, you expect vertical asymptotes. In fact, we're going to see something a little bit different for at least part of that. So we'll leave a little space there. We've got our first derivative, y prime is 5 over x minus 5 squared. I remember doing that one out by hand. It was really ugly. You're lucky we were giving this to you. And then y double prime, second derivative is negative 10 over x minus 5 cubed. I will say this. If you're doing this, if you're stuck on a test doing this, then as far as the derivative is concerned, what I would do is write that as 5 times x minus 5 to the negative second. Because now you just have to use the chain rule instead of using the quotient rule here. The quotient rule there will work. It's just a whole lot of unfun. All right. Well, let's play around with this a little bit, and we might notice something about this. First things first is that I'm going to factor out the negative from the denominator. Write it the negative of x squared minus 25 over x squared plus 5x. And then I'm just going to move that negative out in front. What else do you think I can do with this function? Factor out an x from the numerator, and the denominator also factors. All right. The viewing audience probably can't hear it, but everybody yelled out x minus 5 and x plus 5, which is cool, because my calculus class knows their algebra really well. Good, thank you. Well, what's that mean? It means like this term and this term, they're just begging to be canceled. Now, you got to remember that our domain is still x can't equal 5 or negative 5. But what this means, because I have this term in the numerator and denominator, is that I'm not going to actually have a vertical asymptote here at negative 5. What do you think I'm going to have at that point? A hole. Now on Desmos, you're not going to be able to see it. You can see it on your graphing calculator, but it should be on your test as well. There should be a hole at that point. So we'll have to keep an eye out for that. You will have a vertical asymptote at 5. So that much is guaranteed. So let's draw that. Oh, wait. Somebody else drew it for you. All right. So we've got a vertical asymptote here at x equals 5. That's part of the shape of our graph. So x equals 5. Let's look at something else. In fact, Brandon, you spotted something like this earlier. What if I took a look at the limit? Let's see. Limit as x approaches infinity of x squared plus 5x over negative x squared plus 25. So I just took this and I flipped around the terms in the denominator. So without resorting to L'Hopital's rule, what would that be? Negative 1. Good. It's just a ratio of the leading coefficients, negative 1. So that's telling me what happens to the function as you go out towards infinity, or negative infinity for that matter, plus or minus infinity. And that gives you a horizontal asymptote. Horizontal asymptote. So that's going to be y equals negative 1. That's this line right here. So the function's eventually going to settle down towards that. There we go. So this is framing your graph. It's telling you what to expect when we look at this graph. Okay. Let's keep going here. Let's look at the derivative. Now our derivative, write it either way you want, 5 over x minus 5 squared. Your derivative can change sign where the numerator equals 0 or where the denominator equals 0. So, okay, that means we have to test points on either side of 5. If 5's not in the domain, we still got to test points around it because this function could change signs around it. So, make myself a little table, x, f, and f prime. And let's see. Here, here. Let me introduce a little notation for you just out of my own convenience. What happens if I tried to plug in a 5 into the function? Undefined. Another way to say something like that, this backwards capital E means there exists. My laziness here, it doesn't exist. All right, that point doesn't exist. Just can't do that there. Nor can we do this point here. The function is just not defined there. But we can test on either side of it nonetheless. So if I test on the left-hand side of this, what would be a point that I could test here? 4. And actually looking at this, I don't have to think too hard. The numerator is positive. When I square something, I get something positive. So I'm not going to bother to put that in my calculator. Positive and positive means the function's increasing. And over here, test something like 6. Again, the square term is always going to be positive. This is always going to be positive. So guess what? It's always increasing. That's the conclusion you get from this. What else? Let's work on the second derivative. So second derivative, x, f, f double prime, 5. So if we look at the second derivative, and that's this right here, again we can play our game of testing and figuring out signs. So I gotta take a look at this to the left of this point, left of 5, and to the right of 5. So just pick some test points. 4 and 6. Sure, we'll test 4 and 6. And we don't necessarily have to pull out the almighty graphing calculator to test these points. The numerator is negative. We just need to determine the sign of the denominator. All right, it'd be, if you put in a 4, 4 minus 5 is negative. Cubed is still negative. But a negative divided by a negative is positive. So it'd be positive here. How about 6? The denominator would be positive. The numerator is negative. Negative divided by a positive is negative. Concave up, concave down. All right, let's put this all together then with our shape. Oh, there's one other thing that I like from you in terms of your graphs. It's nice to know the intercepts of a graph. So our y-intercept. How do you find the y-intercept of a graph? Set x equals 0. So y would equal 0 squared plus 5 times 0 over 25 minus 0 squared. Basically, you get 0 and 0. X-intercepts. Set y equals 0. Now, the thing about rational functions, they'll equal 0 where the numerator is equal to 0. Basically, you can kind of ignore the denominator. So I get 0 equals x squared plus 5x. And one of these points we kind of already knew, right? This could be equal 0 when x is equal 0 or x equals negative 5. That's going to be the two places where your graph crosses or touches the x-axis. Let's see if this information matches what we see out of our graphing calculator. We've got a lot of information about where the function's increasing, decreasing, concave up, and concave down. So, how do we put that all together? Well, we can plot our points, right? We've got a few points here. X is 0, y would be 0, x is negative 5, y is 0. So let's put those in. 0, 0, negative 5 and 0. Let's see what that graph looks like. See, does this match all our information? I'll shut these off. So there's our asymptotes, and here's our graph. Now it's kind of hard to see, and it's a little annoying too. Let's see, we got 0, 0. And guess what? We actually don't have anything at negative 5, do we, right? No, we don't. Because at negative 5, we've got a hole in our graph. So that second point there, I kind of forgot when we looked at this. Our second point, second intercept, it's really not there. because the function has a hole in the graph. So it does go through 0, 0. It is concave up, and then approaches its x-asymptote, or x-intercept. So let's graph that there, and finish this thing up. Let's see, is this one good? Yeah. Let's graph it this way. It's like that, and then over here on the other side, approaches the y-asymptote like that. Nice. Now, one thing that you want to keep in mind when you do these things, you can look at your graphing calculator. It doesn't hurt. A lot of people just do all the work and they don't look at their graphing calculator at all. Your graphing calculator should match your results here.